Hi, my name is Rob Erdmann. I'm senior scientist at the Rijksmuseum and a professor at the University of Amsterdam. And today I'm going to be giving you a behind-the-scenes tour of an effort to capture Rembrandt's most famous painting, The Night Watch, at a resolution of 5 micrometers. That will then result in an image that's 717 gigapixels. And I'm going to be talking about how much Python and the open source environment surrounding Python has helped me to achieve this goal. So here is The Night Watch. It was painted by Rembrandt in 1642. It's probably his most famous painting. It shows a militia company that was charged with guarding Amsterdam. And the thing to understand about this is that it's really big. It's 379 centimeters tall, 453 centimeters wide, and it weighs 337 kilograms. So if you prefer imperial units, that's 12 and a half feet tall, almost 15 feet wide, and 743 pounds. So we're going to try to image this at incredible detail because this is part of what's called Operation Night Watch, which is a multi-year project to perform very in-depth, comprehensive research about the painting and its current condition, and then to design a conservation treatment to ensure that going forward, it looks its very best and that it stays beautiful for as long as possible, indefinitely into the future. So this project requires an incredibly large number of people and a huge amount of resources. And so I'd like to give special acknowledgement for all of our various generous partners and sponsors, some of whom which wish to remain anonymous, without whom this project could not happen. I would also like to give thanks to Łukasz Langa and the Python community. I was working in front of the Night Watch using a Jupyter notebook. Łukasz, who's one of the core developers for Python, was taking a tour through the Rijksmuseum, and he spotted that I was using Jupyter and Python. And so he tweeted it, and then this got picked up by many other members of the Python community. And ultimately, it was spotted by Guido van Rossum, who is Dutch, of course. So it's kind of nice that the city where Python was invented is also the subject of this talk. So if you're going to capture an image of a painting, to photograph the painting at this incredible resolution, this is a really hard thing to do. And the reason that it's so hard is that when you have a macro photography camera, so you're going to get very, very close to the painting and capture the whole painting in a grid of photos, there's a very, very narrow depth of field. And so what this means is that if the painting is a little bit too far away, your photo will be blurry. And if it's a little bit too close, it will be blurry. So we have to have a very elaborate system that allows us to sense how the painting is situated relative to the camera, and then to move the camera perfectly into place so that we can capture a photo that's perfectly sharp and color accurate. So one thing to notice about this Operation Night Watch campaign is that the entire thing, both the research phase and the subsequent conservation treatment, are carried out entirely in front of the public. So this painting is basically the centerpiece of the museum, so it has to be visible at all times. So you can see here is a glass house that's a sort of glass box that's built around the painting so that the researchers can carry out their work inside while the public can see them. And although the museum is closed at the moment, we're hoping that it will reopen shortly, and then we can welcome the public back to watch all of our research. You'll notice here to the left and right of the painting are a very large pair of vertical bars, and then an 8-meter long or 26-foot long beam. And this beam can be moved up and down. Here is a view of that as a Cad rendering. And here's a person for a scale. So on this beam, which you see now below the painting, there is a kind of sled that we can move left and right. And here you see the back view of that. So this bit here can move left and right. And again, the beam can move up and down. And then if you would zoom into that sled, you can see that it is also quite elaborate. We have places where we can attach the lights. We can put an imaging laptop in this little cubbyhole here. We can put a power supply for our lights. over here. And this bit is called the orbital frame. This gives us 3 more degrees of freedom. The first is we can move in the Z direction, which is closer and farther away from the painting. We also have 2 rotational degrees of freedom. So we can basically tilt our head left and right. So that's rotation around the y-axis, or yaw. We can also tilt the head up and down, and that is rotation around the x-axis, or pitch. But the interesting thing about this is that we can rotate around the painting. So we can change the direction that the camera is facing without looking at a different location on the painting. So then on that orbital head, we mount the world's highest resolution digital camera. This is a Hasselblad H6D camera. And surrounding that is an array of distance sensors. And then ultimately, we also have the rendering of the imaging location here, which when viewed from the painting outward at the camera shows the region that we're going to be imaging. So this one photo, which is 100 megapixels, is going to capture this rectangle here, which is only 5.5 centimeters wide. So that's about 2 inches wide. So here is a picture for scale where I'm reaching up. And then here is the view of the power supply, the pair of lights, the camera, the imaging laptop, a webcam that's over here. And then we also have a laser sensor that's down here. So this is the hardware that we have to work with. So next I'm going to describe the architecture of the system that coordinates all of the motion of the camera and the captures and so on. So here you see it illustrated with a big block diagram here. The system has 5 main parts. Central to all this is the control subsystem, and that's what is coordinating the motion of the camera and all the sensors in the imaging frame subsystem. It coordinates the command to take photos, which is done over here by the image capture laptop. It writes its log files in real-time telemetry, which it's receiving from the imaging frame subsystem into a high-capacity NAS, which is the fourth part, rather. This is also where we receive all of the high-resolution images. And then there's the computer system that I'm sitting in front of, and that's illustrated in blue down here. This is mostly the connection that I'm using is a Jupyter notebook that gives me a real-time control with status and control widgets that are all running asynchronously, talking up here. So this is the appearance of the control system. This is all done with IPy widgets. And the nice thing is that the Jupyter notebook is all running inside an async IO event loop. So I can have other cells in which I'm doing my work while seeing real-time status updates about the velocities and positions of all of the motors and everything else. So here's a picture of what that looks like in use. So here you see side by side my use of Jupyter with this IPy widgets control system. Here's the view from the webcam that's riding along behind the camera. And then here is a view of the latest high resolution image that I've captured. So to describe all of the working parts here, I'll just describe the process by which a single photo is taken. So to begin with, I'm sitting in front of the laptop down here, and I will command to take a photo at a particular location. So that location is then translated into a region on a previously made 3D capture, laser capture that I'll describe later, so that the control system then does a robust estimation with scikit-learn of the approximate distance and orientation of that patch of the painting. And then it communicates to the imaging frame subsystem via an async IO connection, which has WebSockets. And then over WebSockets, we're using protocol buffers in order to tell the imaging frame to pre-position the angle and distance of the camera to the painting. And then when it arrives in place, it performs a set of sensing with this high precision hybrid image laser rangefinder. So it gets to the approximate position, and then you see here a laser scan. This then allows me to record the positions, the distance to the painting at 15 positions, which have been very carefully placed to cover the field of view of the main Hasselblad camera. That then gives me a set of 15 distance readings, which get aggregated here into the telemetry bundle and sent back to the control subsystem, which again uses this set of 15 measurements to estimate the shape of the surface very precisely. And then, knowing the region of space that will be perfectly sharp in front of the camera, we make a final adjustment to position the camera so that the painting is in that so-called depth of field. So now we're positioned to take what we think will be a very sharp photo. And then the next step is via PyZMQ, a connection to the image capture laptop that's running along with the frame. That is mainly controlled by this Python process here. We're talking via PyZMQ, and there's an async IO event loop here. So what happens over here is that now we've received a command to take a picture. But the problem is that the software that connects to the camera, sort of the tether software, which is called Focus by Hasselblad, doesn't have an API. So we can't just tell it to take a picture. Instead, we have to use a Jython-based open source software called Seculi X to basically do screen reading via OpenCV into the Focus software. So it can see where the buttons are, and it can see where the dialogues are, and so on. And so this will then tell the camera to put the mirror up, tell the camera to capture a photo, and interact with dialog boxes for file naming and these kinds of things. And then meanwhile, this system is waiting for a raw image to show up on the local storage of the capture laptop. So then the next step is that we use PyVips and PyTorch to load the raw image. And there's a neural network that's basically tasked with assessing the focus quality of the image and to ensure that the flashes have both gone off. And then if the image is good quality, then Focus is told to develop the image, which means that it has to apply a color profile, which will ensure that we have perfect color management for the whole thing. And when the image is developed, this process will shovel it down to the high capacity NAS and report back to the central control subsystem that the capture was successful. And then we can move on to the next location. If the capture was not successful, then we take it again after repositioning the camera, because there's sometimes wind on the painting, just air currents in the room, and it's a 17.2 square meter sail in a way, so it can move away and closer to the camera. So the first bit of that system working was the idea that I had a low resolution 3D map of the shape of the painting. So for this, again, SciPy is an integral part. Both SciPy.spatial and all of its algorithms, KD trees, and so on, as well as data shader to help make nice visualizations. So here you see the system without a camera, and you see these 5 laser rangefinders that are positioned around 1, 2, 3, 4, and then there's another one here in the corner. So what I can do one time only is I drive that up and down and left and right across the painting and gather around 20 million points. It's very, very noisy, these points, but I now have a point cloud, which I can then aggregate using pandas and SciPy.spatial and visualize using data shader and ultimately get a nice 3D map. That then shows us something like this. So this has been vertically exaggerated by a factor of 10, but as you can see, there's ripples along the left and right sides of the painting, and the painting bulges out, as you might expect for something that's so heavy, and of course it's hanging vertically. So with this, I have a sense of the approximate 3D shape of the painting so that I can get it into position when I'm ready. And then the next necessary piece for me to capture a grid of photos is that I have to have a good knowledge of the location of the depth of field of the camera. So to be more precise, here's a schematic of the camera, and with an approximately to scale representation of how far away it will be from the painting. So when you set the camera on a given aperture and you've focused it so that you will be capturing 5 micron resolution photos, then what you find is that if you were to try to capture a photo of an object that's too close, it would be not sharp. If it's too far away, it would be not sharp. And then there's a little sort of Goldilocks zone here called the depth of field, within which the image would be acceptably sharp. So there's one specific distance at which it is the sharpest it can possibly be. Now, the problem is that I don't know where this is relative to the camera, so I have to measure it. And for that, I've developed a technique that uses a procedure called shape from focus. So the idea is that I'm going to capture a depth stack. I'm going to take a series of photos where the camera is closer and closer and closer to the painting without adjusting the focus of the camera at all. And when I do this, when the camera is too far away from this flat calibration plate, which is designed to be very reflective and very, very flat, then the whole image will be blurry. And then as I'm moving the camera forward and forward and forward, taking a photo at every step, there will come a moment when part of the plate is sharp, as you see here, the depth of field and the calibration plate intersect. And so here, the bottom of the photo would be sharp. And then if I move the camera still closer, in this cartoon, the middle of the photo is sharp. And then later, even closer, the top of the photo is sharp. So if I would monitor the overall sharpness, then it would look something like this. So how do you monitor the sharpness of a painting? Here, again, I have a PyTorch, a stack of convolution filters with nonlinearities that has been trained to estimate the local sharpness. So this outputs a number for each patch that I put in. So I cut up the image into patches, and for each patch, I see that it's blurry, and then it will come into focus as I'm moving the camera closer and closer, and then it becomes blurry again. And so if I map that across the entirety of the image, of the field of view across, in this case, 41 different photos, then I have a sense of the distance at which this would be the most sharp. And ultimately then this can be fit using scikit-learn with a plane with robust estimation, for example, Brandsack estimation, to tell me exactly the region of space that is in focus. And then I can position the camera, as shown in this middle image here, so that the entirety of this calibration plate is sharp. So I have just the right angles and just the right distance, so the entire plate is sharp. And at that moment, I can use this laser rangefinder to capture those 15 distances across the field of view. That would look something like this. So the calibration plate is white. And then I can set that as the datum, meaning the geometry that exists here, where the plate is perfectly sharp, is the same relative geometry that I would like to establish in the painting for when I park the camera in front of the painting. I don't have the time to take 41 photos at every location because I have 97 rows, 87 columns, which is 8,439 100 megapixel photos that I have to capture. So what I do is I learn how to become sharp in front of the calibration plate, and then I will use these distance sensors to reestablish that same geometry at every location of the painting. So I'm always at the right distance, and I'm always at the right angle, so that the whole field of view will have the painting inside this depth of field. And then the last step to make this whole thing work is that I have to be able to capture the colors that exist in the painting very, very accurately. So I have light sources that may give an unwanted tint to the painting. And of course, the camera sensor, although it's really excellent, it may also have quirks about how sensitive it is in different wavelength bands. So this means I have to do color calibration. Python to the rescue again here. There's a really excellent library called the Color Science Library. I'm also using a non-Python piece of software, but it is open source, a color management system called Argyle. So to do color calibration, what we do is we get a color card, like you see here, being very meticulously cleaned by Leila Sauvage, one of our conservation scientists. Then we mount this next to the painting in the same geometry as the painting, and we use our imaging system to capture this very accurately. Now, before this, we've also done spectrophotometry, so we know the exact reflectance curve of each of these patches. So we then have a ground truth, the true color of each patch, and we have the color of the patch as it occurred in our photo. So what we need is to find out how to adapt a photo as captured so that the colors are what they should be. So here's a visualization of that using Seaborn, in which I'm seeing the ground truth and the as captured color for each of those 140 patches. So you can see as captured, it's not great. Then we use Argyle to build a color profile, and this color profile will take as captured colors and bring them into alignment with the proper colors. And then I can use the color science library to calculate the so-called delta E value. That's the human perceptual color difference between what was captured and what I should have had. And these are numbers here where a value of less than about 2.3 is not detectable by humans. So again, I'm using Seaborn here, and then I can visualize the corrected colors to see how well they're matching the true colors. And so ultimately, we also make a lot of statistical plots that show us things like here's a rug plot showing the delta E values and affirming that all of the colors are less than 2.3 of delta E. To be archival quality, you have to have the maximum delta E less than 10 and the average delta E less than 4. So you can see we're doing a really good job with color management. So these pieces allow me to drive all over the entire painting, capturing 97 rows and 87 columns of the painting. Each photo is 100 megapixels, 600 megabytes on disk. And the entire process of moving into place, sensing the distance, adjusting, taking a photo, checking its quality takes about 23 seconds. So a little bit less than 3 photos per minute, and I have 8,439 photos. So now let's suppose I've collected that entire grid. Well, now I need to somehow stitch them together, but I need a ground truth for the shape of the painting. So these high resolution images have to be hanging on something where I know what the true shape of the painting is. So to do that, again, Python is a big help. Here you can see that before it was installed in the glass house, we secured the painting very securely and photographed it from across a long hall, the main aisle of the Gallery of Honor. And before we did that, we put a series of 4 fiducial marks on the corners. So you can kind of see these little white dots here, but zooming in. So this is basically just a sticker that's placed outside anything that was painted by Rembrandt, which has a little target on it so that we can identify it in the image, and also pins. So what we can do then is on the photo, we can measure the exact coordinates of each of those 4 fiducial marks. And then we physically measure the pairwise distance between each of the pairs of corners. So all 4 sides and then 2 diagonals, basically. So then this is an optimization problem. So scipy.optimize.least_sq allows me to solve for the XY coordinates in a true millimeters space of the 2D coordinates of each of these corners, which I can then use to compute a homography to take the overall captured image and to bring it so that the fiducial marks appear perfectly at the true coordinates. This then means I have a so-called rectified image that I can use to hang the higher resolution images on. Now, an intermediate step that I'm not talking about today, because it's very similar to the 5-micron step, is that I also collected 20-micron resolution photos. So this was 528 photos instead of 8,439 photos. And this was an image that was released to the public about 1 year ago today. So the procedure is we're going to take the 20-micron images and hang them on the overall photo, and then we're going to take the 5-micron images and hang them on the 20-micron photo. Okay, so now let's look at how an image is placed on a ground truth lower resolution photo. Python, again, is a major component of this, and this is based largely on neural networks. So here's the painting again. Let's focus on the face of the main figure, Banningcock. So here it is. And if you would now look at this in terms of the individual captures, here you can see one capture. You can see that we have a small amount of overlap. Any more would have made the number of photos go way up. And now the question is, how can I place this one photo, which is 5.5 centimeters wide, onto the lower resolution image where I really have confidence of the shape? So here you can see the problem illustrated with the green channel. I have the low resolution anchor image, which is fixed, and a high resolution capture. And I want to know how can I position and deform the high resolution image so that it's perfectly with subpixel accuracy positioned on the low resolution anchor. So the first step is to have a pair of neural networks that are each operating on an individual tile. So here you can see a tile from the low resolution image and a tile from the high resolution image below it. One neural network, by which I mean a convolutional neural network that has a stack of convolution filters with nonlinearities, though the convolution filters are constrained so that they always have rotational symmetry, because when I filter this image, I want to make sure that there's no lateral or vertical shifts. So I learn a convolution filter to apply to the low resolution tile, and I learn a second nonlinear convolution stack to apply to the high resolution tile, where the objective here, in terms of the training of the neural network, is to find a pair of filters such that when I do a normalized cross correlation between these filtered images, and by that I mean you slide them past each other and see how well they match, that there should be one and only one offset at which the correlation is really excellent, and at all other offsets, the correlation is nearly zero. And then the last thing to mention about this is that cross correlation gives me what you might call in a Bayesian worldview, a likelihood for where I will find it. And then I also have a prior belief about the relative offset between the two tiles. So I can multiply the two using Bayes' law, and that will give me a posterior estimate that tells me exactly how I should shift the high resolution tile to make it match the low resolution tile. So I cut up the two images where they overlap into a lot of little tiles. In this case, they're 2048 pixels on a side. And I performed this calculation to find the relative movement between the two tiles across the entire image. And now I have an estimation problem to figure out what overall movement would I have to apply, what geometric transformation would I have to apply to the high resolution image to make it align with the low resolution image. So I'm basically going to estimate this with a homography. The homography is all the kinds of transformations that you might encounter upon moving the camera. So scales, rotations, changes in aspect ratio, and perspective effects that will shrink part of the image while enlarging the other part. So I'm using OpenCV, which has a very nice homography estimator, very fast and efficient. And then after I apply that homography, that will give me something like this. So still close, but not perfect. So then the next step, so this is close, but not good enough because I want to be sub-pixel accurate. So then I switch to lower resolution tiles or smaller tiles, train another set of neural networks to learn how to filter these appropriately, again, so that I have one offset that's very likely and others that are not so not viewed to be likely. And then that allows me to make an overall deformation field. So here you see the X offset and the Y offset. So now in principle, I know exactly what homography I need to apply to the image to make it match. I also know what kind of rubber deformation after the homography is applied to make them match with sub-pixel accuracy. So then I have to actually implement that. I know how to move the images, but I don't know how, I haven't done it yet, basically. So to do this, I use a relatively new library from Google called Jaxx, mostly because I wanted to teach myself how to do this. And then after doing some experimentation with it, I found that I could make a much faster interpolation algorithm with Jaxx than with any of the other GPU libraries that I tried. I find Jaxx to be a real delight to use because it has an API that's almost identical to NumPy. So I can do things like Jaxx numpy.where instead of numpy.where, or Jaxx numpy.abs instead of numpy.abs. And then there's another cool feature, and that is that if you write your interpolation kernel, as you see here, so that it only takes a single coordinate at which I want to interpolate into my, my as captured image, then you can make this automatically map across spatial dimensions or batch dimensions with this VMAP decorator. And then finally, I can do just-in-time compilation with this, which will basically optimize the whole thing, distill it down into an XLA kernel so that it runs super fast on the GPU. Just to give you a sense of the timings here, I can take an image, a 100 megapixel image, and 100 million, approximately 100 million different locations at which I want to do an interpolation, and then do this high order interpolation, which requires looking at 7 by 7 different points for each interpolated point. The whole interpolation happens in 45 milliseconds. So, okay, so now I've warped each of the images and I know where they belong. But now I need to, I've got them, so they're all warped. They have exactly the right orientations and scales and so on, but now I need to fuse them all together. So again, Python figures quite heavily in this. In particular, Shapely is a really excellent library for doing computations with geometries, finding areas and perimeters and intersection shapes and cutting a shape with another shape and so on. Network X is a wonderful library that implements very efficiently lots of graph theory algorithms. PyAMG is the algebraic multigrid solver for solving partial differential equations and other large linear systems. And PyVips is really the meat of this. That's a Python interface to the really excellent Vips library that enables one to do computations with images that are far larger than memory. So I'm using pandas behind the scenes for managing the identities of the images and their positions and so on. Then I can use Shapely to see exactly what the overlap structure is of the images after they've been deformed into place. And this then lets me calculate which pixels are under contention, by which I mean, for some pixels, I only have one photo that tells me about what's happening there. But for other pixels, I have, for example, here, I have 2 opinions about what color that pixel should be. And for others, I have 3 opinions. And for others, I have 4 opinions. So what I need to do is find a way to settle the dispute when more than one image claims that it knows what's happening at a pixel, and in fact, to blend smoothly across them. So I can use Shapely to give me the overlap structure. I can then ask Network X for a so-called graph coloring to divide this into the minimum number of sets that are not self-overlapping. So you can see it's done that here with into 4 different sets. So I have the the red team, the green team, the blue team, and the yellow team if you want. That looks like this for the little 10 by 13 image sample that I showed you. So none of these images overlap with each other, none of these overlap with each other, and so on. And now I need to fuse these together. So the fact is that when you're doing photography, the pixels near the edge of the image are typically less accurate. They may suffer from vignetting or lens distortion, even though we have very good control over those. Still, if you have an opinion from one image, which is at the edge of the image, and you have an opinion from another image, which is at the center of the second image, you should prefer the pixel that's at the center. A pixel on the corner is typically very low quality, so you should sort of double penalize that. So the way I solve that problem is for each image, I solve a Poisson equation with a constant source term. So in other words, all of these regions are assumed to have a constant Laplacian, a constant second derivative, a constant curvature. So this is a visualization made after a solution with PyMG that shows me how heavily I weight each pixel. What is the value of each pixel? Here is that when you fuse them all together among the 4 different groups. And then ultimately, I'm going to blend them together using something called scale space theory or a Burton-Adelson Gaussian Laplacian pyramid. And so the basic idea there is that there are large-scale trends between the images, such as the overall brightness trends that I would like to smooth out across all the images because I don't want that each photo is slightly brighter on the right side. But the small scale details I want to blend together over a very small distance. So scale space theory allows me to do this decomposition by doing a series of Gaussian blurs. And then the differences of those successive Gaussian blurs are telling me what I took away. So ultimately, I can then use PyVips to do this series of Gaussian blurs and then to blend the images together, to blend the small scale features together over a small length scale and the large scale features over a long length scale. And then that allows me to assemble the image in different chunks. These were made according to the desires of our researchers, which parts they wanted to look at. And then ultimately, these can all be output into one enormous image. So with that, I will show you the final result. This now is an image which is 925,000 pixels wide, 775,000 pixels tall, 717 gigapixels with a resolution of 5 microns. So that is, to give you a sense of what 5 microns means, the diameter of a human red blood cell is 8 micrometers. So one of my pixels is smaller than a human red blood cell. So you can see now that I can zoom in and in and in, and it's a virtual microscope into the entire painting. I can see every single detail of every retouching. So these are repairs that have been made to the painting. I can see the beautiful paint work. For example, if I zoom in here, I can see how Rembrandt had multiple different wet paints on his palette that he used to paint this. If I look nearby, I can see that there is a pigment particle. This is a smalt particle, which is ground up glass. Really, every little detail of every brushstroke and the detailed condition of the painting. So it's often said that this is Rembrandt, Rembrandt self-portrait that he painted himself in. That may just be an urban legend. But I like to think that it's Rembrandt. And if I go all the way in, I can see the exact details of the brush strokes that were used to make this look like a glossy eyeball, and so on. So we haven't released this image yet, but we will be doing so soon. So yeah, when I was growing up, I was obsessed with this toy called Light Bright, and it let you take these little transparent, translucent colored pegs and push them through some black paper to let some light shine through. I used to play with this for hours on end. That had 214 pieces. Ultimately, in 1979, I made my mother, who is a software engineer, teach me how to do programming. And so I've been obsessed with computer graphics and computer vision ever since. So in the spirit of how it started and how it's going, started with 214 pixels and it ended with 717 billion pixels. So with that, I would like to thank you very much for being such a wonderful and welcoming open source community. I couldn't have done any of the stages of this process without Python and the incredible environment, the ecosystem of open source libraries to do imaging and color computations and data science and visualization and so on. So again, I would like to thank the Python community, thank the organizers for inviting me to give this talk. And I would like to thank you for your attention. Thank you very much.